Okay, ready? So we're going to do a problem using our gas law. Alexander Despati lets one rip 10 meters below the surface of the pool. If the bubble has a radius of 0.5 millimeters upon release, what size will the bubble be when it reaches the pool's surface? Okay, so this is what we can call a classic problem with a series of assumptions that need to be made. And it's very important to understand these assumptions. The first time around, don't get intimidated if you don't see those assumptions. Sometimes when someone's teaching you, they can, or in the book, they can sort of, I think, underestimate, okay, whether it's obvious or not that these assumptions are reasonable. Okay, so I'm going to start off. Okay, ready? So the idea is, the idea of this type of problem is you have a bubble, and the bubble starts off at the great depths of the water, and then it floats to the top. And we know that when you're little kids, right, you draw a little picture of a little fish, and the little bubbles, you know, they get bigger as they come to the top. I don't know why we do that. We all just think that that's the way it should be. Well, let's see whether we were right when we were like first grade. So what happens is the bubble's created, and then it floats to the top, and we're going to prove that they get bigger. Okay, so how do we do this? Okay, well, we only know one equation, don't we? Okay, the equation we know, that's okay, is going to be equal to PV is equal to NRT. And what we have is the pressure at the bottom, I'm going to say PB, and the pressure at the top. And we're going to do this classic way of solving the problem where we're going to write down the ratio. So P top, volume top, number top, moles I mean, R, that's a constant, temperature top. And we're going to have pressure at the bottom, volume at the bottom, the number of moles at the bottom, R, and temperature at the bottom. And then we can take a ratio. Okay, great. That sounds great. Now, where come the assumptions? Well, the first assumption we're going to make, I'm going to write that down over here. Assumption 1. You don't have to write this down when you're solving the problems, okay? It's just for you to learn. Assumption 1 is that, I mean, you could just write down N top is equal to N bottom. What does that mean is that the number of molecules in the bubble doesn't change. The molecules aren't disappearing out of the bubble. They're not diffusing into the water, or the bubble's not picking up molecules. So the number of molecules that the bubble starts off with at the bottom and the number of molecules at the top are going to be the same. Oh, great. So what does that assumption allow us to do? It allows us to cancel those two. Oh, great. Okay. Hey, by the way, I mean, R is a constant, so that cancels. Hey, that makes it good. What about the temperature? So as the bubble climbs, does the temperature change as it increases as in height? And the assumption 2, so this is number 1. Assumption 2 is that temperature at the bottom is equal to temperature at the top. Okay, that the temperature doesn't change. And so once we can write that down, we can also cancel those two temperatures. So we rewrite the equation P top, V top is equal to P bottom, V bottom. We can do that. Why did I do that? Okay, we're trying to solve what? The volume, or the radius at the top, the size of the bubble. Size of the bubble at the top. So we need the volume at the top. You know what I'm going to do? I'm going to erase that, and I'm going to say P top. So if we knew what the pressure at the bottom was, the pressure at the top, and the volume at the bottom, we could figure out the volume at the top. Okay, so let's see. What's the pressure at the top? It's equal to 1 atmosphere, which is equal to 1.013 times 10 to the 5 Pascal. What's the pressure at the bottom? It's going to be equal to 1 atmosphere plus rho GH. That makes sense, right? That height. Okay? And so we're going to plug all that in, and we say 1.013 times 10 to the 5 plus density, 1,000, gravity, height. And they told us 10 meters. Let me erase that. 10. Okay, so we can plug that in to our calculator. Second. Okay, and we get, let me see, 1.993 times 10 to the 5 Pascal. Okay, so we've got pressure top, we've got pressure bottom, and we need volume bottom. So what's the volume bottom? The volume bottom is equal to 4/3 pi r bottom cubed, right? So if we plug all of that in, we get let's see, what do we get? We get 5.24 times 10 to the minus 10 meters cubed, I guess, right? Next. So if we plug in this number, we plug in this number, and we plug in this number, what are we going to get? So we get that the pressure, okay, we could plug in our numbers, and we get that volume at the top is going to be equal to, okay, let me see, pressure at the bottom, 1.993 times 10 to the 5. Volume at the bottom, 5.24 times 10 to the minus 10 divided by the pressure at the top. 1.013 times 10 to the 5 Pascal. Oh, I'm not plugging the units. All the units are correct. I plug that into my calculator. I get 1.031 times 10 to the minus 9. But they asked for the radius, so we have to use the fact that volume top is equal to 4/3 pi r top cubed. Solving, what I like to do is I say r top cubed is equal to 3 VT over 4 pi. That makes sense? Then I plug everything in. Actually, okay, if you want, after I write that, I typically say, okay, cube root. And I plug everything in. And we get 6.6 0.27 times 10 to the minus 4 meters, which is equal to 0.627 millimeters. Ta-da! R top. So what did we say, or we figure out? We figured out that the radius of the bubble was 0.5 millimeter when it was at the bottom of the pool, but when it came to the top 10 meters up, its radius increased to 0.627 millimeters, so it got bigger. That's the problem. So what I show is I showed one way of doing the calculation, and that's just called turning the crank. Okay, so but the mathematics of it all, but the assumptions, and don't underestimate that. Okay, the assumptions are that we had to know that the temperature didn't change as the bubble went up, higher up. We had to assume that the number of molecules didn't change. We had to also know that the volume of the bubble was V was equal to 4/3, okay, pi r cubed. We had to know that. Okay, so there were lots of things that we had to pull out to do this problem, and the first time around that can be tricky, but after you've seen it, okay, you've got to know these assumptions. And so you'll also see maybe somebody else show you how to do it, and you can get intimidated if the mathematics, you can't follow the steps. You don't have to follow the same steps that I followed. In fact, every single time I'll do it, I might do it a different way. Okay, and you too, right? So I've printed out another way. I mean, this is like typically when you see something typed out, because it's so monotonous and difficult to typeset formulas, people have found they tend to do it in an extremely efficient way. And don't get intimidated when you see in text a calculation, and they seem to do it in 3 lines when you might take 6. Okay, that's very common. Okay, so here, for example, this would be an example of, you'd say, this is how you do it, and you'd say, oh well, P1 V1 is equal to P2 V2, and so I guess they're saying that the pressure at the top might be P2, volume at the top V2, pressure at the bottom V1, volume at the bottom V1, P1, right? And so what they did was they plugged in the equation for volume, okay, 4/3 pi r cubed. Over here they plug in the equation for the volume at the bottom, where you plug in the number that you know the answer to, and the pressure at the top, you plug in your number over here, and at the pressure at the bottom, you write it down as 1 atmosphere, 1.01 times 10 to the 5 plus rho gh, and then you plug those numbers in. So you just simply plugged all of the numbers in, and then you have this big equation, and you say, oh, we've got to solve for this. And then nothing's written down, just solve for R2, there's the answer. So nobody would be able to go from that second to last line to the last line like that. Okay, you typically will write some more out. Okay, so something to take into account.